So density of water is 62.4 pounds per cubic foot. What that means is, I think you've noticed that when you dive down into water, the farther down you go, the more pressure you feel. So probably you've all been like 10 feet down in a pool, and you start to feel the pressure, especially in your ears. Okay, so in order to figure out the pressure, you take the weight density times the depth. So this stands for fluid pressure. This is the weight density. And I really don't like this, but the book does it, so I'm going to do the same thing as them. H stands for the depth. To me, H stands for height, but they use it for depth. So for example, if you're 2 feet down in the water, you would take the 62.4 times 2, and that would tell you that at a depth of 2 feet, you feel 124.8 pounds of pressure per square foot. So that's 62.4 pounds per cubic foot times 2 feet. So if you do that, the dimensional analysis, one of these feet cancels with one of those feet. So you get 124.8 pounds per square foot.
Bless you.
Okay, so that means that if you're 2 feet underwater, every square foot of your body feels 124.8 pounds of pressure. Now that seems like a lot. You don't really feel 124 pounds. And the reason for that is right now, you're feeling a lot of air pressure. So there's a bunch of air on top of you that goes all the way up to there, way up to the top of the atmosphere. So there's a lot of air pressure on you right now. So you're used to a lot of pressure. So 124 pounds is not that big a deal because that's what you're used to, sort of. It's more than you're used to, but not that much more is what it sounds like. Okay, so then if you wanted to know the total amount of pressure on you, the total amount of pounds of force, you would have to multiply by area. Because if it's 124.8 pounds per square foot, then you'd have to multiply by the number of square feet to get the number of pounds of force that would be on you. Okay, so that's the formula we're driving at here. Force is the weight density times the depth times area. Okay, so a rectangular fish tank has a bottom that is 6 by 3. Rectangular fish tank has a bottom that's 6 by 3. So that's a pretty sizable fish tank. 6 feet this way, 3 feet this way. Not huge, but pretty big. And water is filled to a depth of 2 feet. So then the question is, what is the pressure, or what is the fluid force felt by the bottom of the tank? Rectangular fish tank has a bottom that is 6 feet by 3 feet. Water is filled to a depth of 2 feet. And the question is, what is the fluid force felt by the bottom of the tank? So we're just going to use this formula, F equals W times H times area. So like we did over here, the fluid force of water is 62.4 pounds per cubic foot. It's at a depth of 2 feet. So then after you multiply that, you find out that it's 124.8 pounds per square foot. And then you multiply by the 18 square feet, because the bottom's 3 times 6 in square feet. So if it's 124.8 pounds per square foot, and you multiply that by 18 square feet, you get 2,246.4 pounds. That's a ton of weight. Literally a ton, right? There's 2,000 pounds in a ton. And also, it seems like a lot. It seems like it's a ton. It's not that big of a fish tank, 6 by 3. The water's only 2 feet deep. But the bottom of the tank has to withstand that many pounds of force. So now picture yourself at the aquarium. And the water, you're going through that tunnel, right? The water all around you. The water's more than 2 feet deep. And it's more than 6 by 3. That's a lot of pounds of force that curved structure is withstanding. It's not glass, it's some type of really strong plastic that they have to specially make in special order. And it's really thick. That's why when you look through it, it looks distorted, like all of a sudden the shark is there and you thought it was there, right? So anyway, that's a lot of force that has to withstand. Okay, now we're going to change up the problem. So that was part A. Now we're going to change up the problem and say, what if the fish tank is filled with gasoline instead? So that's not good for the fish. Okay, so not good for the fish, but it's going to make a point. So what if the tank is filled with gasoline instead? And so I need to tell you what the weight density of gasoline is. It is 42 pounds per cubic foot. So the only thing that's going to change is the W over there is now 42 pounds per cubic foot instead of 62.4 pounds per cubic foot. Did you know that the gasoline is lighter than water? It is. That's why you can't fight a gas fire with water, because you spray water on it and the gas just rises above the water and continues to burn up there. The water will not smother a gas fire. So you need a special fire extinguisher to fight a gas fire. Okay, so anyway, so that's 42 point, what's that? No, I brought it up.
No, so if a car explodes, then why do firefighters put water on
Well, they might be fighting a fire. Maybe the car is on fire.
Yeah.
And so the water is heavier than the metal or plastic that's burning. But if it's gas on the road that's burning, they wouldn't pour water on it. They would use a special foam substance or something.
Don't we have fires on the ocean?
Yeah, so that's why there might be oil floating on the top of the water, and then that's burning on the top of the water. Good. Okay, so 42 pounds per cubic foot times still a depth of 2 feet, right? And still 18 square feet. So that comes out to something different. It's 1,512 pounds. So still a sizable amount of force. The point I'm trying to make is if the substance that you're dealing with isn't as dense, then it's not going to be as much force. Okay, so all of that was not calculus. That was just physics. And so now we need to frame this from a calculus standpoint. Here's where the calculus comes in. What's going on, the bottom of the fish tank, that entire surface is at a depth of 2 feet. But the side of the fish tank, every bit of that side is at a different depth under the water. So this might be nothing deep, then half an inch deep, then an inch deep, then a foot deep, then 1.5 feet deep. So as you go down the side of the fish tank, every bit of the side of that is at a different depth. So the depth is constantly changing. So this 2 right here can't stay as a 2. It needs to continuously change. And then, so that's where calculus comes in. We have a depth that's constantly changing. So we're going to need that formula. Or we're going to need calculus in order to figure out the pressure on like the side of a fish tank or something like that. Okay, so that brings us to example 2. So we're going to have a dam in the shape of a V. (24 feet across the top). And 16 feet high in the middle. Has a gate six feet below the top of the dam. So we're going to, and the gate is oh, I'm sorry, this problem does not have a gate. Let's see. A dam in the shape of a V, 24 feet across the top and 16 feet in the middle. .4 feet across the top, 16 feet high in the middle. How can I salvage this? And the water level is 6 feet below the top of the dam. Probably should have just started a new sentence there. Okay, so now the question is, find the total fluid force on the dam. Dam in the shape of a V, 24 feet across the top and 16 feet high in the middle. My English is not good in this sentence. Are you understanding what I'm trying to say? Mm-hmm. All right, cool. And the water level is 6 feet below the top of the dam, and we're going to find the total fluid force. Okay, so let's draw this thing. It's in the shape of a V. It's 24 feet across the top and 16 feet tall. So behind that is a lot of water that it's holding back. So there's like a lake back there that this is holding back. So it's concrete or something, holding back a bunch of water. And the water level doesn't go to the very top. The water level is like here, 6 feet below the top. And what we need to figure out is how many pounds of force is being exerted on this dam on the front of it. Okay, so like I said, the problem is that this bit of water is at a different depth than that bit, which is at a different depth than that bit. So we need a variable that represents how deep down in the water you are. So I'm going to have that be y. Y represents the depth. So that little bit of water there, at a depth of y, experiences a certain amount of pressure. Just like at 2 feet down, to figure out the pressure you feel, you take 62.4 times 2. So at a depth of y, the pressure felt is 62.4 times y. Then we need to multiply by the area, because this is a certain number of pounds per square feet. We took 62.4 pounds per cubic foot, multiplied by feet, so now we have pounds per square foot. So we need to figure out how much area there is at that depth. So we're going to draw in a thin little rectangle there, and we're going to find the area of that rectangle. Now that presents a problem, right? Because now all of a sudden our rectangle has some height to it, and so the depth at the top of the rectangle is a different depth than at the bottom of the rectangle. But later on, we'll make the rectangle infinitely thin, and then we won't need to worry about that. So for now, what we're figuring out is the area of that rectangle. All right, so we don't know how wide it is. That keeps changing. Like down here, it'll be a different width than that. So I'm going to call the width x. But we can call the height dy. So that's x, and that's dy. So the area is x times dy. So now here's what's happening. This formula gives me the amount of pounds of force on this rectangle here. Not on the whole dam yet, just on that little thin rectangular part of the dam. So I took 62.4 pounds per cubic foot, multiplied it by feet, so that gave me pounds per square feet. Then I multiplied by the number of square feet, and so I'm getting altogether the number of pounds of force. Again, that's only the pounds of force on that little rectangle. So I need to find the pounds of force on this rectangle here and the one right under there all the way stacked up, right? So I'm going to add up all of those little forces to get the total amount of force on the entire triangular dam. Okay, and then we got to figure out what our bounds are. This is dy. So y starts at 0, at a depth of 0, and goes down to the bottom, which is a depth of 16. No, sorry, that's not right. It's a depth of 10. Do you see why I would have been tempted to say 16? So the water starts at a level of 6, so it goes from 0 to 10. Is everybody doing okay? Yeah.
Why would we do 6 to 16?
If we had, we could have made a choice where y represented the distance from the top of the dam down, and then yes, we would have gone 6 to 16. But I chose for y to represent the distance from the water level down. And so that's why I went 0 to 10.
Okay.
But you can make that choice when you do the problem if you want. It's going to change this. So there's other repercussions to making that choice. Okay. Great question. Everybody else okay with this? There is something that's not fabulous about this. What's not fabulous about this? There's an x there, and we need to get rid of that x because we need y's. We need only y's in our equation. All right, so in order to get rid of that x, I'm going to draw some triangles. So the first triangle is going to be the entire dam, which I kind of already have drawn, but it's getting kind of messy. So it's 24 here and 16 across the middle, right? And then the other triangle I'm going to draw is this one. So that's x across the top. And then I need to figure out what this is. Okay, so this is y. I'm going for this. This is 10. So this is 10 minus y. Is everybody okay with that? I'm labeling the height of this triangle as 10 minus y. Okay, so now these triangles are similar. So I can set up proportions. So 24 over 16 equals x over 10 minus y. Then you cross multiply. So 16x equals 240 minus 24y. So x equals 15 minus 3 halves y. 240 divided by 16 is 15. And 24 divided by 16 reduces to 3 halves. So now I can take that and plug it in for x here. So I've got the integral from 0 to 10, 62.4 times y times 15 minus 3 halves y dy. Now I'm going to distribute this. So that comes out to, I think it's 936, but I better double check. Yes, 936. So I'm integrating from 0 to 10. 936y minus 93.6y squared dy. Oh, thanks. I've told you guys my joke where none of you pay attention to me, and now I have another object in the room that refuses to pay attention to me. Have I told you that yet? Ridiculous. Everybody doing good? So from there, it's pretty easy. You just take the antiderivative and plug stuff in. Yeah, sorry.
I'm just wondering, does it matter what x you use? Is there a reason you did 10 minus y for your x? Like when you fix that triangle, does it matter what smaller triangle?
Yeah, I mean, that x and that 10 minus y triangle, that represents all of the other triangles. So I'm getting a relationship, given the y, what the x will be in relationship to that. Yes. I mean, I focused on the one that I was looking at, but it does represent all of the triangles. Good. Okay, so antiderivative of that, I think you can do that. It comes out to 15,600 pounds. Everybody still doing good? Okay. Let's see, what else do I need to mention here? couple of the problems have some equations that are a little bit difficult to deal with. So we're just going to practice writing an equation. So we're going to write an equation for the ellipse. And the ellipse is going to look like this. So actually it's a half ellipse. And I want it 12 feet across the top. And then I want it 7 feet here. Okay, so it's been a while since you did this. Does anybody know the general form for the equation of an ellipse? Fair enough. It's x minus h squared over a squared plus y minus k squared over b squared equals 1. Can't believe you didn't remember that.
It was on the board.
So what do the h and the k represent? The center of the ellipse. So let's go back over here. We don't have an x-axis and a y-axis, right? In our picture. So we can place the x-axis and the y-axis wherever we want. So what I'm going to do is I'm going to put the x-axis here, and then the y-axis here, and then the point 0, 0 is the center of my ellipse. So I'm strategically placing the x-axis and the y-axis so that my center is 0, 0. And then that's going to make that equation over there a lot easier. Okay, so that means that I can put x squared over something plus y squared over something equals 1. I'm going to figure out the somethings in just a second. This is the stage I'm at right now because I plugged 0, 0 in for the center. Okay, so now the A over there represents kind of like a radius, but not exactly a radius. It represents the radius in the x direction. So the radius in the x direction is here, and that's 6, right? Half of the 12. So that means the A over here is 6. So that means this is 36. And then the B represents the radius. It's called the major axis. The radius in the y direction. So what's the radius in the y direction? 7. So that means it's going to be over 49. So this right here is the equation for this ellipse. This is the equation for the entire ellipse. We didn't have the other half on top. This represents the entire ellipse. So there's one question where you have to write the equation of a circle, which I think you can handle a little bit better, but the ellipse, I knew you didn't have a shot at remembering that. For a circle, what's the general form? Yeah, x squared plus y squared equals r squared. And if there's a center that's not 0, 0, it's x minus h and y minus k. But you're going to make it so that the center is 0, 0. So you can write x squared plus y squared like you said. Is everybody doing okay? Are you sure? Okay. I think that's all I have, but let me check through my notes to make sure I didn't leave anything out. Yes.
So for the X and the ellipse equation, or for the A, sorry, it doesn't matter that radius is technically going to change at the bottom of the ellipse. It's still going to be very strict.
A represents the distance from the center of the ellipse
Okay.
out to the farthest edge on the x-axis. That's called the minor axis. There's a small, on an ellipse, there's a smaller radius and a larger radius. Sometimes it's oriented the other way. But in this case, the A represents the distance of the minor axis. And the B represents half the distance of the major axis.
Makes sense.
Good.